Humans are biologically hardwired to comprehend the true scale of existence. To our brains, anything smaller than a grain of sand simply gets filed away into a mental folder labeled tiny. On the other extreme, anything larger than a mountain just registers as huge. Our physical intuition hits a wall. To bypass this limitation, we rely on a mathematical tool called orders of magnitude. By stepping up or down in powers of 10, we can shrink the incomprehensible into numbers we can actually use. By riding this mathematical ladder from the absolute smallest limit of physics all the way up to the largest, we can map our true place in reality. We'll start by looking straight down, diving past cells and atoms to find the absolute floor of the physical world. This graphic shows a meter being divided over and over until we hit a number with 34 zeros before the 1. 1.6 times 10 to the negative 35th power meters. This is the Planck length. In frameworks like string theory, this is the point where the concept of distance literally stops making sense. You cannot cut space any finer. The Planck length acts as an indivisible cosmic pixel. It provides a hard mathematical floor to reality itself. Surfacing from that subatomic basement, we return to the familiar, visible world. Consider a single human hair. Depending on the person, it measures anywhere from 17 to 181 micrometers across. This narrow band of micrometers and meters is the sliver of reality our brains actually evolved to navigate. But jumping 10 orders of magnitude upward, we leave the human scale behind entirely and enter the realm of megameters. This is our macro home. From pole to pole and across the equator, the Earth measures roughly 12.7 megameters in diameter. Moving from the width of a hair to a 12.7 megameter rock reveals how incredibly localized our daily existence is, hovering right in the middle tier of the cosmic scale. Once we push past our atmosphere, terrestrial units like meters and megameters become completely useless. The void is too vast. We have to adopt the light year, the distance light travels in a single year, which equals an immense 9.46 petameters. To grasp this, imagine shrinking the Earth down to the size of a single grain of sand. At that scale, how far would you have to walk to find the nearest star? This visualization scales the gap for us. If Earth were a grain of sand, the next closest star would be another grain of sand resting nearly 30 kilometers away. This violent leap into petameters destroys our terrestrial sense of proximity. It exposes the deep physical isolation of our solar system within the galaxy. Scaling up another 10 orders of magnitude brings us to the absolute limit of what we can physically observe in existence. This diagram models the observable universe. It is a massive sphere with a diameter of about 880 yottameters, or roughly 93 billion light-years across. This boundary exists because of a strict physical limit created by the speed of light itself. Information cannot travel any faster. Since the universe has only existed for about 13.8 billion years, that light has only had a finite amount of time to travel through expanding space to reach our telescopes. So this edge doesn't necessarily mean we've hit the end of all space. It is a hard informational ceiling dictated by the laws of physics. Comparing a 17 micrometer human to an 880 yottameter universe triggers a sense of existential dread. At these scales, our mass doesn't register as a rounding error, but that feeling of insignificance ignores a massive intellectual triumph. A biological species trapped on a 12.7 megameter rock successfully figured out how to calculate the mathematical gap from the 10 to the negative 35th Planck length all the way to the 10 to the 26th observable horizon. We are not a meaningless mote of dust. By mapping these staggering orders of magnitude, we have found our exact place in the cosmos.